Great, welcome everyone. Thanks for having me. So I'm James Ward. I work on developer experience for QDeveloper at AWS. So that's my background. That's my day job. For fun, I like to mess around with structured concurrency and other sorts of things. So this talk is about structured concurrency. I'm going to be showing a lot of different languages and frameworks and libraries for doing structured concurrency. And so you all may not be familiar with all the languages and frameworks that you're going to see. So please stop me if there's something that doesn't make sense. If the Scala syntax is weird, which it is, I can explain it. So just let me know, and we'll go through and learn about structured concurrency. So let's start at the high level. What is structured concurrency? So it's a little bit different than normal concurrency, where what we're trying to do is say that kind of the structure, the hierarchical structure that we've written our code in should adequately model the concurrency model that we're trying to achieve. And so an example of this is we've got kind of our main program, and then we're going to open a scope. And we're going to say, okay, anything that goes into this scope now is part of that scope. So we're going to put things into a scope. And then the structure of this says that when all of those things complete, then our scope is completed. So we wait at this point where we're not going to continue with the rest of our program until all the subtasks within that scope have completed. So this is kind of the basic form of structured concurrency. There's a really great blog post that one of the, I think, initial creators of some structured concurrency library stuff wrote a blog post called, I think it's GOTO Considered Harmful. Does that sound right? Maybe somebody even remembers the exact title. Did I get it close? Anyways, so the author of this came up with a library in Python that used exactly this kind of paradigm for defining structured concurrency. And in that terminology, in the Python terminology, it was called a nursery. The nursery was the scope. And so you'll hear different terms for basically the same sort of thing as we go through. But this is the idea, is that our code is going to model this hierarchical structure. And then ideally, we get some benefits by doing things in this way that are beyond the more lower level concurrency primitives that you may be familiar with. We're going to look at error handling. We're going to look at resource management. We're going to look at some subsets of structured concurrency. And so let's go into the first subset. So one of the most useful places for structured concurrency is to define a race. And this is not a race like a race condition. This is a race like a running race or a horse race. And what happens in a typical race in structured concurrency is the same thing. We're going to have our scope with our child tasks in it. And as soon as one of these tasks completes, that's going to end the race. So unlike a normal race where everyone gets to finish, in the typical race in structured concurrency, as soon as someone wins, everyone else is just canceled. And we just take all the other tasks and say, hey, you don't even need to finish the race. Actually, you shouldn't, because I don't want you to use resources if you don't have to. And so in a race, we just cancel the losers, essentially. And the winner is the thing that comes out of the race. And that's the thing that we're interested in. And that's what allows our program to continue progressing. So does anybody have any ideas for what races are useful for? Anybody using races in their programs? Yeah. Yeah, so do you have any ideas for where that would be used? So I'll give one, unless anybody else has one they want to throw out. But you're exactly right on why you would use a race. So go ahead. You maybe could use a race for that to model, like, I have two drivers, they both have two different things going on, and I'm going to see, I don't know, who clicks the button first or something like that. So yeah, you maybe could use structured concurrency to model that. Exactly right. So a good place where this is often used is I've got my database, and then I've got a cache. And it turns out that sometimes just going to the database will be faster. And so why don't I just make 2 requests at the same time, one to the cache, one to the database, and whichever one comes back first, I don't really care. Like, it doesn't matter where the data came from. Another example of this is maybe I have 2 different AI models, and I want to query them both. And maybe one's going to come back faster than the others. And so there's lots of different places where once we have this ability to race things, you start to see lots of different places. Like, I probably could reduce my P99 latency in a variety of ways by using a race. And so a race, probably one of the most common ways that we use structured concurrency, especially for back-end systems. And so I'm going to go through some code for races, now that you kind of have a high-level idea of what the race is. But to do that, I have this suite of all sorts of different implementations of structured concurrency. It's called Easy Racer. So the idea was like, how easy is doing races? That was the initial idea for it. And so there's a server for Easy Racer, and the server has a bunch of obstacle courses in it that the clients then try to implement. And so the clients are making HTTP requests to the server, and the server is trying to validate, did you do the structured concurrency things correctly? And there's a lot of different implementations now. I've built a bunch of the Scala ones and Kotlin ones and Java ones. Got some help with the Rust one, and there's a Go one that I didn't write because I'm not very good at Go, and all sorts of other ones. So you can go check out the GitHub repo if you're really interested in like TypeScript effect. Then you can go check out that one. Today I'm going to focus on the ones that I'm most familiar with. So this is the JVM languages, Scala, Kotlin, and Java. So there's these obstacle courses, and the obstacle courses are going to validate that you're doing structured concurrency in the expected way. And this will help us learn about some of the aspects to structured concurrency, and then some of the different ways that different languages and frameworks address those. So let's talk about some just broad structured concurrency ways to do it. And there is the scope-driven, which is what I mentioned earlier, the initial Python implementation with a nursery being the scope. And in the world of Java, underneath the Loom umbrella, there is a new Java enhancement proposal, 453, that adds a structured concurrency scope into the world of Loom. You don't really have to use it with Loom, but it makes the most sense in Loom. Loom is virtual threads on the JVM. And so we're going to see this approach today, but and then there's many others that use the scope-driven approach, so the Python one and others as well. But we're also going to see another style, which is called direct style or imperative style, which is a style that makes it look like you're not really writing concurrent code, but it is concurrent. And so, and that's most of the time in the JVM world implemented on top of those virtual threads in the JVM on Loom. I'm not going to show the Rust one today, but the Rust one is kind of a similar approach to this direct style. And then there's an approach called effect-oriented. I will talk a little bit about effect-oriented, but I just finished my book, Effect-Oriented Programming. So if you really want to dive into effect-oriented programming, I'm just going to say, talk to me afterwards or get my book to really dive into that, because it's a pretty meaty subject. But we are going to see a little bit of it today because I'm personally excited about the effect-oriented approach. And so we'll see it with 2 different libraries, Scala-Zio. Well, actually, I'll just show Scala-Zio today. And then there's another one called Scala-Kio. And the Scala-Zio one is a monadic effect library, and then Scala-Kio is an algebraic effect library. So both of those for Scala. Okay, so different approaches. You're going to see a lot of this in code. So let's dive into the first obstacle course in Easy Racer to show what this actually looks like in code. So in the first scenario for Easy Racer, what we're going to do is we're going to race 2 concurrent requests. So I have my server, and I'm going to open a connection to the server. I'm going to open a second connection to the server, and then whichever one of those connections responds first is the winner. And then the other connection should be canceled. So that means it should be closed once the race has been completed. And so we're going to see what this looks like in different libraries. I'm going to start with a pretty straightforward implementation here, which is using a library called Ox for Scala. This is built on virtual threads. And so let me actually jump over into IntelliJ so we can actually run this thing and see it working. But so is that font big enough in the back? Read that okay? Awesome. Okay, so here's my Scala program. You can ignore like these parts. That's just getting the URL that I'm going to connect to. So here's the interesting part. I'm defining a function that's in Scala that's a def, and it's called rec. And then I'm going to make a request, which you'll see there's just some boilerplate here that I didn't want to repeat. But this is just my HTTP library for Ox. And then I'm going to send this request, and then I'm going to get the body. And so you'll see this looks very imperative. This is the direct style. I'm not having to think about that scope stuff we talked about, which we will see in a little bit. I'm just writing this as imperative code. But at this point, all I've defined is a function, right? This is just the function. And then there's a function in Ox called race success. And I'm going to pass in rec, which means call this function rec and then call this function rec. And that's how I'm going to get the two concurrent requests to my server. So those both happen concurrently. And then I want one to come back, and then I want to cancel the other one. So let's go ahead and run this thing so that we can actually see if it's going to work here. I am running my server over here, so should connect up to my server. So you'll see that my server's just logging like, okay, number of concurrent connections. So a connection is made from the client. I've got one concurrent connection. Then a second concurrent connection is made. So now I've got two open connections to the server. And as soon as I get, in this scenario, as soon as I get that second connection open, then one of those connections will respond and say, hey, HTTP, okay. And then it will return a string to me. And for all of my scenarios, what I'm trying to get to is a string that says right, like you got the right answer. So, but then we'll see that, okay, the first connection that responds, that sent the right HTTP body, then you'll see that we went down to 0 connections, and we couldn't quite see the timing, but sure enough, as soon as this race had been completed by the winner, then the other rec, so let's go back to the code here, that second rec, maybe it was this one, we don't know what order it happened in, but that second one then will be canceled. And then the cancellation of that request will close the HTTP connection to the server. And that's why we went down to 0 concurrent connections. But what I get out of this race is just a single string. So you'll see that what I get back is just a single string. So normally a rec would give me a string back. And I don't want strings from both of them. I just want the first one that I get back. So that's our very basic race here with Scala and Ox. Questions about the basic race or any of the syntax or any of the scenario stuff? Yeah. It's a good question. So yeah, there definitely can be overhead to doing a race. And so the good thing about having the cancellation is that as soon as the winner is determined, then we should tell everything to stop. Like don't keep going with what you're doing. Stop what you're doing. So if you're doing a database query and that query is taking a lot of resources, if I've gotten a winner, then stop doing that. So, but yes, there definitely is overhead to doing multiple things instead of just doing one thing. So I think I mentioned it a little bit earlier, but one of the goals of a race is to reduce your latency. So if you want to get down that P99 latency number, a race can be one way to do that. But maybe you don't want to send 2 requests every single time or multiple requests every single time. And in just a little bit, we'll get into something called hedging. And with hedging, it's a way to deal with there maybe sometimes being high latency, and we want to deal with that particular problem. But good question, yeah. Certainly there can be overhead to doing unnecessary work that you may not need to do. Yeah, go ahead. So the cancellation piece could mean a number of things. There is an example, which I won't get into today, in Easy Racer, that actually cancels like a tight loop of execution within my code. And so most structured concurrency libraries and frameworks have a way to do that kind of cancellation. Most of the time when we're talking about cancellation in terms of a service that we have called externally, is we're going to close the connection. And so the server needs to know how to deal with the fact that a connection can be closed at any time, and hopefully it's doing the right thing, cleaning up the resources, stopping doing what it was doing, that sort of thing. But it is up to the external system, in this case, that it handles a connection closed correctly. It's a really good question. So not in this framework, but in the effect framework that I'll talk about a little bit later, there is a way to tag certain side effects as being uninterruptible. So maybe you don't want cancellation to actually be just like, hey, close your connection, stop doing what you're doing. Maybe you want it to actually wait until it completes. And so in that case, you would have to know that this is something that shouldn't be interrupted, but then you can tag it and say, this is uninterruptible. Do not let this thing just be closed. And so it does depend on what semantics you want. I think that's what you're highlighting, is that the systems that you're talking to and integrating with may have different constraints for cancellation and what you need to do there. And you are going to have to become aware of that. But I don't think it's much different than outside of structured concurrency. Anytime you are enabling a connection to close or enabling something to be canceled, you're going to have to think about the ramifications of doing that. So, but yeah, great question on do you always want to interrupt? And maybe you don't, and that's okay. You can still have a race, and there is actually a way to do a race with uninterruptible things that will allow them to complete. Maybe you fork it off onto a daemon thread and let it complete on a daemon thread, or maybe you block your whole process, the continuation of your process, until that uninterruptible thing has completed. So there is different ways to manage that, but you do have to be aware of what the cancellation could mean to your system. Good question. Okay, so that's our basic race. Let's hop back to some other examples so you can see some different approaches to a basic race. So the next one is using a library for Java called JOX, and JOX is actually created by the same creator as the Ox library, but this time for Java. And you'll see that kind of similar semantics here. In Java, it's a little bit trickier to define a function like I did with the def rec. So I just repeated the function code that's going to make the actual request there. But essentially the same semantics. I'm using this direct style. We haven't got into the scope-driven approach yet. So I'm just saying, hey, send off these two requests, whichever one happens first. Great, give me the result of that, and then cancel the one that didn't, the loser. And that all happens great there. I will pause here to see any questions on JOX before I go on to some different approaches. Yeah, go ahead. Yeah. Yeah. We'll talk about error handling in just a minute. So I think there was two different things you brought up there. One was about kind of debugging, tracing, that sort of thing. And then the other one was around error management. So we'll get to error management in a second. But let me touch on the tracing part of it. So in the world of Java Loom, they have in virtual threads, they've made it so the stack traces are logical across the virtual threads. And then some of the other systems that are not based on Loom necessarily have other ways to be able to do essentially tracing across async boundaries. And so some different approaches for how the kind of tracing piece to this works. depending on the language and framework and that sort of thing. Okay, so that's JOCs. I think there's a whole lot more to JOCs, but this is just the basic race in JOCs, which is pretty nice if you're in the world of Java. Okay, so now let's look at just straight Loom. So this is if you're on the JVM, you don't want to use a library like JOCs, and you're doing Java. You can use that new JP, I forget the number, 453 or something, and this has the scope mechanism built into it. And so this allows us to establish a scope. So first we're going to set up our request, our builder for our request. But now we're going to do a try with resources on this structured task scope, shutdown on success, and what we're going to get back is an HTTP responsive string. So now we've created a scope. We are in a scope in that try with resources block. And now we need to put things into that scope, put processes in that scope. And so we do that with a scope.fork. And you'll see very similar to what we saw before, I'm going to put in essentially a function that's going to make my request. I'm going to put in 2 of those. And then the scope.join is essentially what says, wait here, don't go any further in your execution until one of those has succeeded. And it's the shutdown on success, which is what determines the behavior of that scope.join. So once we have finished past this mark, then we're going to get the result of the race and return that. So that's our just raw, like no library on the JVM, Java language. It does require this experimental JAP for structured concurrency, but that's what the scope approach looks like. And this is very similar to other scope-driven languages, like a lot of the Python stuff uses these same semantics for how they create the hierarchy of structured concurrency. Okay, any questions on the straight Loom structured concurrency pieces there? Yeah, good. Good questions. Thanks. Yeah, so it is this like higher level abstraction over threads, and you really should use this with virtual threads, with the Loom virtual threads. Because the Loom virtual threads allow us to not waste threads if we don't need to. So this is all non-blocking underneath the covers. I'm using blocking APIs for HTTP. This scope.join is blocking, but the magic of Loom is that I'm not actually using threads when I'm just waiting on those resources remotely to respond. So this is what Loom is really doing for me, is making it so I can write my code in a way that seems blocking and like I'm going to waste threads. And underneath the covers, Loom says, no, actually, we can suspend and give that thread to somebody else to be used. So this, even though you can use that structured task scope outside of Loom, you probably wouldn't want to. You really want to use this because you don't want that scope.join to just be wasting threads for no reason while it's just waiting on these HTTP responses to come back. Good question, though. Okay, so that's the Loom approach with scopes. Kotlin, I love Kotlin. There's some great stuff around structured concurrency there, but it doesn't have a race out of the box, which is kind of interesting. They do definitely have support for structured concurrency, but they don't have the semantics of a race. But we can create our own race using the select is the structured concurrency API that we can build a race on top of. A select allows us to say like, all right, I'm going to put a bunch of stuff into a scope, still kind of scope driven here. I'm going to fire off those tasks. That async keyword is what says, all right, go off and do that, and then go off and do the second request. And then I do have to set up some kind of error handling to handle the cancellation semantics that I want from a race. So unfortunately, in the Kotlin, the coroutines library for Kotlin, there isn't a race out of the box, but there are a couple libraries with races that are built on top of this in the world of Kotlin. I won't show it today, but if you're into functional programming, the Arrow library for Kotlin has a really great race, and I do have an easy racer implementation of Arrow. And then there's another library called Splitties that has a pretty good race in it as well. It's structured concurrency in the terms of a race is about going from many to one thing right? I could have many racers and I want to get to one winner. That's what the race is for. Not Kotlin coroutines kind of specialty there. It is focused more on the many-to-many, or being able to do a bunch of things concurrently and then be able to get to the end of a process and cancel everything, or wait at some point until everything is finished, which I think maybe later I'll show another example of that. Okay, so that's Kotlin coroutines. Now, Scala Zio, I did want to show this one because this is the effect-oriented one. And there's something a little different about this approach. And in this one, what I'm doing is, you may notice here that my rec is not a def, but it's a val. And this is a very important thing about the effect approach, is that effects don't actually perform behavior. They don't perform effects. You have to take effects and run them through an effect system in order to get the behavior to actually execute. And so this val rec, it isn't actually doing anything. Like you remember the def rec before. When we called def rec, it actually made the request. Val rec just is a description of something to do, and then we have to run this through the effect system in order to take this description and actually produce the result. And there's some really nice things that we get, which we'll see a little bit later, about when we define things in terms of this effect that then gets executed by the effect system later. But you'll see this code does look pretty similar to the ones we've seen before. It's just a little different API. And there is an API where we can say race and give it 2 recs. But there's another API where any effect can be raced against any other effect. And so I'm just saying rec, race, rec. And that's setting up it's actually creating a new effect, which is a effect that has the race built into it. So that's the effect approach. We'll see kind of a more compelling example in a little bit. But let's move on to the second scenario. So in the second scenario, now we get to error management. What if I start off my race, so I've got my 2 concurrent connections to the server, but then what if one of those connections just dies, just gets closed? And how do I handle that? So that's the scenario 2 here in Easy Racer. And there's 2 different approaches that we can take to dealing with errors. The first one is something that's called shutdown on success, or there's different API names for this, but we'll see it in the Java one as shutdown on success. So what shutdown on success says is that we've got our scope, we've got our children in our scope, and as soon as we get an error on one of those, so let's say this happens first, so the first thing to happen is we get an error, well, we just consider that child to be a loser, and we keep the race going. So the race doesn't end just because one of the racers fell over, died, or threw an error, whatever. So we just keep the race moving, and then the next task that actually completes successfully, then that is triggering the end of the race, and so that's the error that then propagates through. And then if we had more children that weren't already errored out, they would get canceled. And so that's the shutdown on success. It means I don't care if I see errors from the racers, I'm going to wait until I see a successful race winner in order to continue and complete the race. So that's the shutdown on success, but there's another variation on this called shutdown on error. And what happens in shutdown on error is as soon as I get an error from one of the child tasks in my scope, then I'm going to cancel everyone and the race completes with an error, throws an exception in the case of Java or produces an error value in the case of other frameworks. So those are kind of the 2 typical semantics for how we decide we want to deal with errors within our race. So let's see some code for this. So it turns out in the world of Java, the code is actually the exact same as the first one. And so the server actually verifies, for Easy Racer, it actually does close one of the connections, and it makes sure that, hey, if you get the right answer in this scenario, that needs to have not actually then canceled your whole scope or canceled your task. And so same code because we are using the shutdown on success for our scope there. And so even now with the server shutting down one of those connections, we still wait until we get a valid response from the other connection in order for the race to be completed. Okay, so that's our Java Loom version of that. Any questions on scenario 2 or the Java structured concurrency example for this, or error handling? Anything I missed on error management? So so good question. So if we have run out of racers, they've all erred, maybe we only had one racer, but we aren't able to get to a state where we have a winner, then the race in most semantics will just complete with an error, or in this case, throw an exception and say like hey, all your racers, no one could complete, and so now we get a race, the race is over, and no one won kind of exception. So by default, the race will most race APIs will just return one error, but there are some different semantics depending on which library you're using if you do want to accumulate all possible errors. Most of the time you only want one error out of a race, but there are different APIs if you do want to aggregate errors. So different ways to manage that. But I don't remember the actual, maybe it's just an interrupted exception or execution exception that comes out of that if all the racers have lost. Was there another question back here? No. Okay, great. Okay, so that's the Java one. So I mentioned the Kotlin splittees library. So just to show you how, again, like some of the stuff in Kotlin doesn't quite have the semantics that I prefer for races especially, but you can do it. And so now I've got to kind of manually deal with the cancellation. So this is saying like hey, if my connection gets closed and it throws an exception, then I need to catch that exception, and now I need to not cancel the race because of that exception. And the way that I do that is I say await cancellation, and that just says, all right, keep trying with your other racers until something works. So not exactly the best semantics for a race there, but you can do it if you need to. Yeah, was there a question? So the race, that race of is what we'll say like hey, like eventually the parent scope may say like all of my racers are dead, and so then that outer scope can actually just cancel all the children. That's a good question, and maybe I have a race condition in my race, and I should come up with a new scenario to test exactly that. That'd be fun. We'll work on that together. But good question. We'll have to test that and see how that actually works in this case. Hopefully I don't have a race condition in my race. Yeah. So you can transform from futures to different Scala APIs. So if you're in the world of Zio, you say like Zio.fromFuture or something like that, and that'll get you from a future into the Zio effect. And then Kio also has transformers from futures to that. Aux, I'm pretty sure that the Scala Aux library also has a transformer from a future, but yeah. One of the challenges with futures is that they, by default, aren't cancelable. And so one of the nice things about some of these other APIs is that you can transform a future into the particular version of structured concurrency that you want or effects that you want, and then that will add cancellation on top of the future. It'll wire in that. Yeah, good question on futures. Okay, let's move on to scenario 3. So scenario 3 is, let's test that we're actually non-blocking. And my little laptop here, let's hope that we can make 10,000 concurrent requests. And that should work on my laptop if I'm non-blocking. I'm not using a thread per connection. And so let's look at what this looks like with the Loom one. So for the Loom one, it's pretty straightforward. We just are going to 10,000 times put something into our scope. So I used a int stream range closed to do the for each on that. But I'm just putting those in and then doing my join. I'm still on a shutdown on success, but that's how we do it in Loom. Pretty straightforward. Anything you put into the scope, it's going to wait there. And so in this case, yeah, we are making 10,000 concurrent connections to the server, and one of those is going to respond and say, hey, you're the winner, and then all 9,999 of the rest of them need to be closed. And that certainly happens here in this case. The Java JOX one, kind of similar, but instead we're not using that scope orientation. We really just come up with a list that has all of our request functions in it, and then we say, all right, let's race all the things in my list. So pretty straightforward there, but more direct style, not the typical scope style for that one. Okay, questions on the 10,000 requests? All pretty straightforward so far. Okay. Scenario 4. So this is where we then get into some interesting things around additional pieces to error handling. For scenario 4, what we're going to do is we're going to race our 2 concurrent connections, but one of them, after 1 second, should have a timeout and should close the connection. And so again, the server is going to wait until you have actually kind of completed the obstacle to give you the right answer. But let's look at what the semantics of this look like. So in the world of Java and the structured concurrency in that new JEP, the way that we need to do this is we need to actually establish 2 levels in our hierarchy. So we're going to have a scope, then that scope is going to have another scope in it that's going to be a child of that scope. So you really can build up a whole entire hierarchy in the structured concurrency. And so let me walk through what's happening here. We've got our outer scope, which is our outer kind of race. We'll look down here first at our just basic request, but then we're also putting into the scope something that is going to make the request but have a timeout. Using this join until is one way to do a timeout. And so we've essentially created a scope within a scope, and once that timeout hits there for this one, that one will then close the connection, and the server says, oh, okay, I did have 2 concurrent connections. After 1 second, one of them closed, and now this is the one that is going to win. So this kind of embedding of scopes within scopes, totally a valid way to use structured concurrency, and definitely a nice thing about being able to build these hierarchies, but not the cleanest way to do things here. Okay, interesting note that I don't know if it's implemented this way, but there is a really easy way to do a timeout when you're in the world of virtual threads or effects, things that aren't blocking threads, things that have a timeout. If you can do a timeout, if you can do a sleep, you can do a timeout. Because if you take a task and then you sleep another task, and then you race those 2 things together, you now have assembled a timeout on top of a sleep and a task. So you race those 2 things and you get to a timeout. So when I'd originally written this one, I'd written it in exactly that way with a thread.sleep, and then I found that there is a join until that gives me essentially the timeout semantics as well. But useful place for a race is to manufacture your own timeout API. Yeah. So in the case of Loom, it's all virtual threads. So everything underneath the covers is going to be non-blocking, not using actual OS threads. So on the actual, so let's take, for example, the network I/O piece of this. There is usually a thread that is based on the read of the socket that then will awaken the code that you're actually executing when there's something to be handled by that. And so that's part of what Loom is doing underneath the covers is certainly managing that. And I'm sure there is some additional overhead to doing this versus being purely blocking, no virtual threads, that sort of thing. Netflix has some good blog posts about their adventures into using Loom and the Netflix infrastructure and some of the challenges that they've run into with that. So, but I think overall, Netflix is pretty happy with Loom for the system performance that they're seeing, other than a few bugs that they ran into. But yeah. Okay, so that's scenario 4. Let's move on to the JOCS version of it. So in the JOCS version of it, we get a bit simpler API because we can just do a timeout with a task, which again is just racing a sleep with the task. And I think that's actually how JOCS is implemented there. It's a nice API for doing that, but all works. Okay, scenario 7. So for scenario 7, this is one of the more useful places for a race, and exactly to the question earlier of, what if I don't always want to make 2 concurrent requests? Well, it turns out Google and their infrastructure does a lot of what's called request hedging, where they say, hey, you know what, sometimes we know that this request is going to take a long time. But it's only sometimes, and we don't want to make 2 requests all the time. So what they do is they track a kind of typical latency, and this only works, I think, for idempotent services, but they track their typical latency, and they say, all right, if in our typical latency window, we haven't gotten a response yet from the server, why don't we just go ahead and send a second request? So they wait some amount of time, they hedge, they wait some amount of time, they send that second request, and then they race the 2 together because maybe it turns out that that first one is going to actually come back faster than the second one. And so this is hedging. So in scenario 7, we start our request, we wait at least 3 seconds, we start a second request, and then we race the 2. And that's what it looks like in the Java world, the straight Java world, is in our second task, we're going to do a thread.sleep. But remember, this is on virtual threads, so we don't have to worry about that actually blocking a thread, and then make the request. And so that's how we would do the hedge in Java with Loom. Okay, and you can go and explore in the GitHub code other implementations of that, but I think you get the idea of hedging and its usefulness in infrastructure and reducing latency. Okay, so let's go on to scenario 8. Scenario 8 is where now we're dealing with resource management. And not all, but a lot of the frameworks around structured concurrency have also added in not just error handling, but also ways to deal with resources into them as well. Because now that we deal with cancellation, we likely need to deal with opening some resource, using that resource, and then closing that resource, and doing that all in the scope of our structured concurrency task. And so in scenario 8, we're going to raise 2 concurrent requests that use a resource that we obtained. So we obtain the resource through a request, and we also have to close that resource through a request. So in the world of aux, this is actually pretty straightforward, pretty nice implementation here, where we've got functions for open, use, and close. And then we do need to establish a scope to be able to manage the when things should be open and closed. And this is called supervised. So I've got my rec-res. This is my like request that is using a resource. So in my supervised scope, I'm going to say use in scope. I give it my open function, I give it my close function, and that's going to get me my ID back, and then I can call my use function here. So that's my def that's going to make the request, and then I can just race those 2 against each other. So pretty nice, straightforward implementation with aux there, and some of the effect-oriented ones are also pretty clean. I will admit, I'm not the best Java programmer. I've been doing more Scala and Kotlin lately, so there's probably better ways to do this, but here's the Java implementation that I came up with, and it's a couple pages long. So we've got our auto-closable where we're managing our state and our scope and are able to make our connections and handle the errors and close and all that kind of stuff. So quite a bit of code there. But then, now that we've got our auto-closable, now we can use our shutdown on success, and we can do our try with resources that's going to allow us to open and close in that try with resources block. And then we can put those in our structured concurrency scope, and then the rest of it looks the same as what we've seen before. But all that works, it passes the obstacle test, and that's all good. One of the things that I think is kind of fascinating, which we'll end on here, is that you can, like, this code is fine. You know, it's reliable. You can read it and understand it. But I tend to prefer code that's kind of more descriptive of the problem I'm trying to solve. And so one of the things that I do quite a bit when I do have to work with code like this, and I'm just curious here, if any of you do this sort of thing, where I've got this big block this is my, let's see, scenario 8. And in scenario 8, I've found that, hey, if there's this big block of code and you don't understand it, I often ask the AI, do you all do this with Copilot or whatever? So let's see how this, in my case, let's go ask Q, explain it. And so it's going to give us, my session timed out, demo fail, got to re-log into Q. So for me, I really like the concise code that like really models the problem I'm trying to solve. And that's my preference with a lot of this, especially with concurrency when things get really complicated. But that's not always an option. And so certainly, if you're dealing with code that can't have those nice concise APIs or use effects, I hope you use AIs to explain to you how the code works, and hopefully your sessions don't time out. Okay, so that's scenario 8 on using resources. I'll go through this last one here, and there's 10 scenarios, but you can go explore 10 on your own, but I will end with number 9. So with number 9, we get into a different model of concurrency where instead of doing our scope shutdown on success, we actually want to go many to many. So I'm going to make a bunch of concurrent requests, in this case only 10, but I'm going to make 10 concurrent requests, but then I want to get all of their responses, and I don't want that scope or that task to be shut down if any of those return errors or anything. And so the way to do this with the Java API is to say, hey, let's just create a new structured task scope. But you'll remember before there was the shutdown on success, and we didn't see shutdown on error, but there's those ways to do it. But then if you want the many-to-many case, in the Loom example, you're just going to call structured task scope, and that will let all of the requests, all 10 in this case, come back. And so in this case, I'm making 10 requests. So you'll see me forking those into there, doing my join. And then I need to, for this particular obstacle course, assemble all of the successful responses in order that they came back, and that's how I get the right answer. So that's what that stream transformation there is doing at the end. So that's the Java version of it. In Kotlin coroutines, it's actually a place where coroutines is actually pretty good, is on that many-to-many kind of use case. And so on this one, it's pretty straightforward. I've got a list of 10 items. I'm going to put my requests into those. And then what I return out is either null or the time that it came back and then the body. And then I can do my filter out the null ones, sort by the time, and then join to a string there. So I think this was the one where Kotlin actually did pretty well with the many-to-many, but not the many-to-one, which is the typical race. So this one is not a race. This is structured concurrency for many-to-many tasks. You want to send off a bunch of requests, let's say, and get all the results back, not get to a single one. Okay, so that's scenario 9. We'll wrap up real quick, and then I think we have a few minutes for questions, right? So first of all, concurrency is hard. It definitely, when you're working with the low-level primitives of concurrency, there is a lot of foot guns and challenges to getting it right. But structured concurrency does make things a lot easier. It does have some constraints for how you do concurrency. But if you can use those higher-level abstractions for structured concurrency, it will significantly help with avoiding deadlocks, avoiding race conditions, which we'll explore that possible race condition later. But use higher level abstractions if you can. If you're in the world of Java, that JOX library is great. If you're in the world of Scala, Scala Zio is great, or Scala Ox is great. And if you're in the world of Kotlin, Kotlin Arrow is great. If you're in the world of TypeScript, there is a Scala Zio implementation for TypeScript called Effect or Effect.ts, which is great. So there are now a lot of times these structured concurrency libraries which give you a lot of the benefits of concurrency with the error handling, the resource management, all that kind of stuff with high-level APIs like races built into them. So use higher-level abstractions if you can, and if you can't, hopefully AIs can help you understand your code. And then I mentioned it before, but I'm an absolute fan of effects. We didn't see it really here, but the race that I could do on an effect can be done on any effect, which is anything that is a side effect, anything that's potentially going to fail, talking to some external system, whatever. And so a lot of great things about effects, giving us a lot of flexibility, great performance, especially with concurrency, that sort of thing. So, okay. So that's my summary. There was a question in back. I think we got, how many minutes do we have?
We got a couple minutes.
Couple minutes, okay.
Anybody got a question?
No?
No?
Okay, any questions about anything? If you do want to look up the repo, it's on my GitHub, and it's called Easy Racer, which somewhere in my repos. So Easy Racer on my GitHub. If you want to check out any of the other implementations. Yeah, go ahead. Yeah, good question. So when would you want to use many-to-many? So this is a place where, let's say that you need data from your account database, but then concurrently you can also fetch data from some geodatabase. Just as an example, you've got two things. They don't need to be ordered. They can be done at the same time. Why don't you put both of those requests to both of those databases, make them happen concurrently rather than sequentially, and you do want both of those responses to come back. You're not doing a race, you really do want both of them, but putting those into a structured concurrency scope will allow you to manage cancellation and error handling in an easy way, as hopefully you've seen, where if one of those services throws an error, if you're in a structured concurrency scope, then maybe you actually want to cancel the other request. And so that's just one example of a place where error handling and cancellation would be helpful in that. But certainly if you can do things concurrently, then you should. And if it's simple concurrency, then structured concurrency is probably the easiest way to do that a lot of times. And to have the resource management and error handling and cancellation, all that stuff built in. Yeah?
So I have my thoughts
On the interruption cancellation stuff?
Not on this, but about the reactive programs, right? So it doesn't do structural concurrency, but you can do stop, arrow, and do some other things around it. I was wondering what's your thoughts on that versus the proper concurrency scopes that actually takes care of all that things for you.
Yeah, I mean, anytime I can hand off to experts and library authors the hard parts around error handling, error propagation, cancellation propagation, all that kind of stuff, I would love to not have to think about that. And so yeah, like I've been doing reactive programming for a long time. A lot of the older stuff requires me to manually manage a lot of those pieces. And so huge fan of the libraries that make it so I don't have to think about those. And so, yeah, did that answer your question at all? And if you have opinions about, I would love to hear them. But well, you're not a fan of reactive?
I'm a fan of reactive, like the core keys, all that stuff. That's my group. Otherwise, you're gonna have to shoot yourself in shotgun.
Yeah, I've spent a lot of time in that world of kind of the more lower level reactive stuff. And I don't have any desire to go back. Like it's too many places where things can go wrong. And so having the higher level abstractions, whether it's effects or jocks or awks, so much better than the pain that we had to deal with. And it really comes down to cancellation, error handling, resource management are kind of the three things. And if you can hand those off to a library to do that all right for you, then do. All right. Hopefully that was useful for you. I'll be around if you have other questions. Thank you.